to present our paper, Audiovisual Separation with Hierarchical Fusion and Representation Alignment, which has been accepted to the British Machine Vision Conference 2025. In the real world, sounds are often mixed and overlapping, for example, a band performance. Traditional audio separation methods, which rely only on audio signals, often struggle in these complex, multi-source environments. This is where audiovisual separation comes in. By leveraging the natural correspondence between audio and visual signals, we can provide a powerful new tool for separating sounds. Our first major challenge is deciding how to effectively fuse audio and visual information. Existing methods primarily follow two strategies: middle fusion and late fusion. Middle fusion integrates visual features early, at the bottleneck of the audio U-net. This strategy is particularly effective for separating instruments with short, transient sounds and simpler spectral structures, like the trumpet or flute. However, it may struggle with sources that are harmonically rich or have sustained notes. Conversely, late fusion applies visual features much later, at the final layer of the audio U-net. This approach is more effective for separating instruments with sustained tones or complex harmonic structures, such as the saxophone, cello, or acoustic guitar. The trade-off is that late fusion may overlook the important transient details that middle fusion captures. As you can see in the figure, instruments with shorter notes and simpler harmonic structures, like the trumpet, are better suited for middle fusion. Meanwhile, instruments with sustained notes and complex harmonies, such as the cello or saxophone, benefit more from late fusion. This clear trade-off highlights the limitations of using a single fusion strategy. This leads us to our second challenge. While existing methods have benefited greatly from using powerful, pre-trained visual models like CLIP, they still rely on the audio branch to learn audio features from scratch. This is a missed opportunity. Large pre-trained audio models, such as CLAP, have already learned high-quality, semantically rich audio representations from vast amounts of data. The question is, why aren't we using them? The challenge is that these high-level, semantic embeddings from pre-trained models often lack the fine-grained time-frequency details that are essential for the source separation task. Simply replacing our learned features with these pre-trained embeddings would likely lead to a loss of fidelity. So, our key question became, how can we leverage this rich semantic knowledge from a pre-trained model like CLAP without sacrificing the crucial spectral details that our U-net needs to effectively separate and reconstruct sounds? To overcome the limitations of existing methods, we propose a new way of thinking about audiovisual separation. First, we developed a hierarchical fusion strategy. This component is designed to combine the complementary strengths of both middle and late fusion, allowing our model to handle a wide range of sound characteristics, from sharp, transient notes to sustained, harmonically rich tones. Second, we propose audio representation alignment. This is our method for bridging the semantic gap between the U-net's internal audio features and the high-quality embeddings extracted from CLAP. By doing this, our model learns to capture high-level semantic knowledge while still preserving the fine-grained spectral details required for accurate separation. Now, let's look at the results. We evaluated our method against several baselines on three widely used datasets: music, Music 21, and VGGSound. The most important metric for sound separation is the signal-to-distortion ratio, or SDR, because it provides an overall measure of separation quality by accounting for both interference and artifacts. As you can see in these charts, our approach consistently outperforms all existing baselines across every dataset we tested. Beyond the quantitative metrics, our method's superiority is visually apparent. This slide shows a qualitative comparison of our separated audio spectrograms against a leading baseline, ClipSep, using examples from the music dataset. The rows show the query frames, mixed audio, the output from ClipSep, our method's output Rs, and the ground truth for various instruments, including the cello, acoustic guitar, and accordion. Compared to the ClipSep results, our spectrograms show fewer artifacts and less interference, more closely matching the ground truth. You can listen to the audio of these samples on our project website. In addition to improving separation performance, our representation alignment method yielded a fascinating and unexpected result. We found that it significantly reduces the modality gap between the audio and visual representations. What makes this so surprising is that we did not introduce any explicit objective to minimize the gap between the audio and visual modalities. In conclusion, our work makes three key contributions to the field of audiovisual separation. First, we proposed a novel hierarchical fusion strategy. By systematically analyzing the complementary strengths of middle and late fusion, we created a single model that effectively separates both transient and sustained sounds. Second, we introduced audio representation alignment. This technique allows our U-Net's audio features to learn high-level semantic knowledge from pre-trained clap embeddings, without losing the fine-grained spectral details essential for separation. Together, these innovations allowed our approach to achieve state-of-the-art performance, consistently outperforming existing baselines on multiple benchmark datasets. Thank you for your time. I am happy to answer any questions you may have.